Alright, welcome to the last video for Chapter 11. Let's see. We're going to finish up with acetylide anions, or alkynyl anions. Okay, we mentioned this before. Now we're going to finish up with this. 11.11 is the reaction of these special anions. 11.11, call them acetylide anions. It's just the deprotonated form of an alkyne. Okay? So we can, big picture, take an alkyne. Because it's sp hybridized, this is the hybridization effect. We can treat this with a base of some kind. We introduced this. We talked about suitable bases and unsuitable bases, basically negative nitrogens and negative hydride, for example. A carbanion would work as well, a regular carbanion, but NH2 minus or H minus are going to deprotonate, and O minuses are not strong enough. Okay, but you get this. And then what can you do? You can react that with some electrophile. Okay, so let's show some actual examples here. Again, it's got to be a terminal alkyne. Na plus NH2 minus. We'll abbreviate this in the future, but draw that out. Looks like LDA. LDA would work as well. Deprotonates. Those electrons go on that carbon. And you get a sodium acetylide, what we call that. Then we can do SN2. So again, we're building on prior knowledge. We can take, I'm showing wedges and dashes, there's obviously no stereochemistry there, but it's the same thing we talked about. So instead of an OH minus attacking, what is happening is backside attack, that's attacking from the back, pushing out the Cl minus. You generate a molecule of sodium chloride. Let's show this product. CH3. You've replaced the H with a CH3. You've done a net substitution, but by deprotonation and then substituting at that carbon. So there's a couple different things going on here. But this is just SN2. Okay, we've seen that before. And your byproduct is sodium chloride. Okay? So, give you a take-home in a slightly different representation. What if I give you this? We said sodium hydride is a sufficient base, a strong enough base, so deprotonate, and then we're going to add ethyl bromide. Okay? So show me that product. Go through the mechanism, deprotonation, SN2, give me the product and the byproduct. Okay? Kind of another take-home assignment. So let's do this starting from acetylene. Acetylene is the simplest alkyne, 2 hydrogens there. What can we do? Okay, one equivalent. You're never going to deprotonate both at the same time, but you can just use one equivalent. CH3I. You're not going to deprotonate both H's and get a double anion is the point. But sodium amide and CH3I. I'm going to leave that up to you, and you tell me what that is. And then do the same thing, NaNH2, ethyl chloride. And I'll give you that product. So sort of take that home and think about how you get to this product. Okay, so we're just doing it twice. Okay, deprotonation. So that's one very useful thing you can do with alkynes, is you can deprotonate them. And you can do SN2 substitution on alkyl iodides, alkyl chlorides, alkyl bromides. Okay, we saw these early on. We didn't make a big deal about them, about acetylide anions, because we had plenty of other nucleophiles. This is just another nucleophile for SN2. Now, building on epoxides, right? We talked about epoxides. Another very useful reaction of acetylides. Acetylide anions is the following. Right? We talked about epoxides and we said the less substituted carbon here is going to react under basic conditions. So we're going to treat this with, let's draw our carbon this time. I'm giving you the anion and telling you that you don't have to deprotonate that. I'm giving you that. Okay, so that was presumably made by deprotonation. And then we're just going to add excess water to quench the reaction. So mechanistically, what happens? This is the same thing, it's just a different representation. Okay, this lone pair is going to attack that carbon. SN2-like, okay, we got two lone pairs on the oxygen, SN2-like. What happens? This it's not a stereocenter, this orientation isn't changing. So if it were a stereocenter, it wouldn't be changing. Okay, but here's the O minus. Okay, put this down here, run out of room a little bit, just so you can see it's SN2-like. That's a straight bond. Okay, there. It's attacking from that face, it's popping open. Okay, and then what happens, you have lots of water in the second step. It's just an equilibrium reaction. It's not this simple, right? You're not just getting OH minus to leave a molecule of water. There's excess of it. Eventually you get to the product. Here I can draw it a little bit more clearly. We're just drawing the protonated version. Okay, notice if that were a stereocenter here, hypothetically, it would have been inverted. Okay, that's inversion of stereochemistry. We'll show an example of that. Okay, so let's go through, let's just do another mechanism. Okay, we're going to do a epoxide on a ring. We have a less sterically hindered site. There's two stereocenters here. Okay, got an anion, got some water to quench things with. What's going to happen? Let's draw the mechanism. Which face is this going to attack from? It's going to attack from the bottom face. I'm going to kind of show this arrow as kind of a dashed. It's coming from the back. Underneath the ring, it's popping that open. Okay? It's SN2-like. Notice this stereocenter hasn't changed. We have two stereocenters to begin with. One of them is unchanged. Okay, this one now, the hydrogen went from being in the back to the front. That's inversion. SN2-like inversion. And then all we're doing is we're adding water, excess. It's just an equilibrium exchange process. That is the final product. Okay. What you get some NaOH that is dissolved in a lot of water. Okay. All right, so that's alkynyl anions or acetylide anions. It's a deprotonated alkyne. It's a nice cylindrical small nucleophile. Works well as a nucleophile. That's kind of how we would rationalize that it's a weaker Bronsted base than a typical carbanion, and it's a nice nucleophile because it's small. It's not very sterically hindered. All right, so let's look at synthesis 11.12. Retrosynthesis. and we want to think through how we can make some things. If you're kind of seeing this, you're seeing how we're building up our bank of reactions, and so the retrosynthesis problems will get more challenging. Okay, let's say we have some acetylene and we want to make this aldehyde, right? The aldehyde on the left, we want to make it from acetylene. So the question is, how do we work backwards from this point, and how do we work forwards from this point? We just talked about what acetylenes can do, so maybe we can deprotonate that, and that could be useful. So sodium hydride, or sodium amide, we call it, NaNH2. We could deprotonate, then we got an anion, right? And then we're looking, we count up, there's 1, 2, 3 carbons. So, I wonder what would happen if we added a CH3Br. What would that give us? That gives us the right number of carbons. That's kind of interesting. So then, how could we convert that alkyne to an aldehyde? The answer is yes, we can. We can use hydroboration. Again, every single one of these, work through the mechanism. Okay, keep practicing. What happens with hydroboration? You get the get the boron to line up over here like this. Why? Because this is the more partially positive. Okay, if we drew a carbocation, it'd be there, and then that boron is going to get oxidized and get converted to the aldehyde. Okay. So draw out these mechanisms. Don't try to memorize all this. Work through this problem. Work through all these forward mechanisms. Let's do another one just to compare methods. Now we have a ketone, acetone. How could we make acetone from acetylene? Okay. And based on what we just said, you could use sodium amide, CH3Br, to do the same idea to get to propyne. But then, of course, we can't use hydroboration, right? To get to that product, we need to use hydration. Okay? Draw out all these mechanisms, all these intermediates. Okay, let's do one that's a little more complex. We'll see in organic 2 ways we can make organic molecules like this, but let's say we started with this. We're going to have to use a chapter 15 reaction to look ahead a little bit, okay? But I'll give you that one. I'll tell you, again, we're just kind of putting it in your mind. If you do Br2 with some heat, and you can do what's called a benzylic bromination. Okay, this position here is benzylic. Okay, next to a double bond is a little bit activated. We'll talk about some of this stuff. Abbreviate this as a phenyl. But now we got a bromide, so we could probably use that, right? So at least that's just again to put in a plug. We're going to see how that works, but now we got a bromide. So how can we convert this bromide to that? Now notice here that, I mean, I'm not going to have you just put on carbons, take them off, and then put them back on, right? This is carbon 1, and that's carbon 2. Carbon 1, carbon 2. This ring is not doing anything, okay? So try to simplify the problem for yourself. What can we do with bromides? We can eliminate them. We can substitute them. There's only 2 possibilities. So do a substitution. See where that leads you. Practice these, and then try an elimination. Okay, what happens if you add potassium tert-butoxide or sodium amide or LDA or DBU, DBN, sodium hydride, etc.? What do you get? Get a double bond. Now this looks a little bit different, right? We have a double bond. We know we can do some additions to double bonds. What can we do with this double bond to get to the aldehyde? Okay, so we're kind of stuck. What do we do with double bonds? Can't remember. Let's work backwards over here, right? Aldehydes. I want you to remember this. If you have aldehydes, you can make them by hydroboration. Okay, hydroboration of something will give you that aldehyde. What is the something? Put our phenyl there. Of terminal alkynes. Okay, terminal alkynes hydroborate and oxidize to give aldehydes. Okay. So how can we get from an alkene to an aldehyde? Or, I'm sorry, an alkene to an alkyne? That's the question. So we're going to need 2 steps to do it, right? We keep working backwards and we say, I know how to make alkynes. We make them by a double elimination of a vicinal dibromide. Okay, so you got 2 bromines. We know we can do that. Then all of a sudden we say, oh, now I can make this by Br2. Okay, we'll talk a little bit about the differences in Br2 with these ionic mechanisms and with radical mechanisms in chapter 15 because there's similarities, but yeah. Okay, so that wraps up chapter 11. Okay, chapter 11 has a lot of similar themes to chapter 10, and then there's got some new things. These acetylenes, these terminal alkynes, you can deprotonate them and use them in a special way. So we will wrap up chapter 11, and then we'll pick up chapter 12 next time.